All right, guys, now we're going to continue, and there's the halogenation reaction. So that's where we take a pi bond and we add a Cl2 or Br2. And most of you remember that goes through a cyclic intermediate where we have the pi bond attack one of the halogens, release the other one, then the one that got attacked comes back. And so we make this cyclic bromonium or chloronium ion. And then the other halide that came out is going to go back and open up the ring again. So we get a 1,2 dihalide. For alkynes then, you might think, oh, well, then I just have an extra pi bond following along, right? So that's true. So you have an extra pi bond at the end. So you have your 1,2 dihalide, but you've got the extra pi bond because you started with 2. But the pi bond here can keep reacting, because if you have excess X2, then you can keep reacting again. And these two products here is very hard to stop if you have excess. All right, and so that's what they're showing you here, is you go all the way down then, and you keep adding X's until it's exhausted. Now the mechanism for this is not well understood, because with a double bond here, there is a lot of ring strain, but there's also the whole reason why we think that this mechanism is true for alkenes, for this part, is because we see trans stereochemistry here. So that's why this mechanism and this intermediate is believed to be true. But when we have an alkyne, it turns out that some situations you see trans, but with other situations you don't. So like if I use chlorine instead, I get something different than if I use bromine, whereas I don't have that with alkenes. With alkenes, it's very consistent. So for that reason, I'm not really going to go through the mechanism here, but I'll just say that it's a little more complicated, and so for that reason, we won't do the mechanism for alkynes for this one. But in lieu of that, go back and review your alkene reaction for the halogenation, because that one you see a lot. Okay, so that's this one here, alkene, bromonium ion that's cyclic, and you get trans stereochemistry. But for alkynes, I'd say don't worry about it. You can still sort of think of it that way. I do. I still think of this as, okay, there's going to be some kind of cyclic ring, and then the X comes in and attacks the more substituted carbon. You can sort of go through those motions, and it will help you see that these are vicinal or next to each other, but you see both of them. You don't just see only major product of trans, you see major and minor product trans and cis mixtures, and then it varies with halogens. So I'd say let's just, for this example, know that you're going to get a mixture, but in any case, usually we just do excess and we go all the way down till we fully saturate with all the X's that we can. So let's take this reaction and add it to your reaction tree. Okay, so X2, and let's do excess, or you could specify 1 mole, but that's usually hard to stop here. But if it says 1 equivalent, then this is what they're talking about doing. So you could do that up here as well. X2, maybe X2 1 equivalent, and then if you want to, you can do another one, X2 again. You know, you could say excess, or you could have different branches, one for excess and one for 1 equivalent. Okay, I'll leave it up to you. It's your reaction map, so you guys can do whatever you like for that. And now we're at oxidative cleavage of alkynes. Let's do a review of alkenes. Oxidative cleavage is when we broke that apart, opened it up, put oxygens in there. So I'll show you that right here. If we cleave that, so just sort of break it open, and then put your oxygens in there where the cleavage occurred. All right, so we're going to end up with a ketone here and an aldehyde here. And then you can pull it out and make it straight, and you've got this as your final product. And of course, the conditions for working this up are very important. The reason why we have an aldehyde here is because we have reducing conditions here. Usually you see a follow-up of dimethyl sulfide or zinc and water. So that's very important in telling me, oh, make an aldehyde here if there's no carbon. Well, ozonolysis for alkynes is a little bit different. It's the same kind of idea where we're going to do cleavage across the pi bonds, but because of the extra pi bond, we are more oxidized than in an alkene because we had to remove more hydrogens, right, to make an alkyne. So because it's already more oxidized, when you cleave it, you're going to end up with more oxidized products than you normally would. So in this case, we're going to use ozone to do the cleavage, and then this piece here is right here, and this piece here is right here, okay? And then the oxygens from ozone added here as normal, but there are no aldehydes present, so you just do not see aldehydes with cleavage of alkynes, again, because we're at a higher oxidation level. Okay, so in this next problem, let's draw a terminal alkyne, and we're going to do oxidative cleavage on this, so let's just practice that. What reagents do we need? We need ozone followed by waterworks. So if we have this kind of cleavage, we've got these two carbons over here, and that's going to form a carboxylic acid. And then I have this one carbon left hanging over here. Okay, so now what do I do with that? That carbon has a hydrogen, but that gets oxidized immediately. And then I end up with this on both sides. That's the way to oxidize, fully oxidize my carbon here. Now, I think some of you guys remember, this is unstable. This is carbonic acid, H2CO3. Do you guys remember how this breaks down in the carbon cycle as well, which maybe you learn in ecology class? Carbon cycle, you have CO2 and water combine and make carbonic acid, and that's usually sequestered in the oceans. So this will break down, and I will end up with water disappearing, and I end up with CO2. Okay, so CO2, and then you have water, but that's already in the solvent, right? So you have water as well. And I drew it bent, but it's linear, by the way. All right, I know it's really bothering me. I really want to fix it, but let's move on. Practice the product of each alkyne reacting with each of these three reagents. So in this problem, what I want you to do is take this first alkyne here and show me what do you get with excess HBr, what do you get with excess Br2, and what do you get with ozone followed by water. And this will be a good way for you to review all those reactions. And as an extra step, practice doing the mechanism while you're figuring out what the product is. And then do the same thing with this bottom one. And let's go through it when you're done. Okay, one tricky thing here is you want to make sure you have the right number of carbons. So I just automatically number it. I have 5 carbon chain. So I do 1, 2, 3, 4, 5. And then I know for this HBr, I add Br Markovnikov. So I'm thinking of adding it here, but I have a 2 pi bond, so I do it twice. So I get the geminal dihalide. For this one, I have excess Br2, so I'm just going to keep adding bromines to both pi bonds until it's exhausted. So Br2 here, and then Br2 again. And then if I had one equivalent, though, and then I would have to make sure I only had one Br here and one Br here, okay? And most likely it's going to be trans as a major product. And then, but I'm going to have a mixture, right? So. And then the last example, I do the oxidative cleavage, but because I have a 1 carbon unit here, that's going to become my CO2. So I'm going to have CO2 for that part, and then the 4 remaining carbons becomes a carboxylic acid. All right, not too bad, right? Okay, so I want you to do the same thing for this one, and check your answer. It's question 9.24 in the book. Okay, so for this last problem, we've got an alkyne that's a C4 alkyne. Alkyne with 4 carbons. It's treated with ozone, and we have a carboxylic acid and carbon dioxide. So what do you think must be the structure of that alkyne in order to make these products? So I think if you've been paying attention, you know that you get CO2 only from a very specific kind of alkyne. So you may already know in your mind what that could be. Otherwise, go ahead and draw out a couple of different possibilities and see which ones would lead to CO2. Then after you figure out which ones it could be, then draw the expected product after treatment with H2SO4, HgSO4. All right, guys, so I think you know that we have to have a terminal alkyne in order to have CO2, and then the rest of the carbons are in a carboxylic acid. So it must be this, and there's no other terminal alkyne you can get because you only have 4 carbons. I was thinking originally while I was talking that if there were any chances for branched out here, you could also have that, but it's with C4 you can't. So then when you react it with acid and mercuric sulfate, you have Markovnikov addition, so you end up with the ketone. All right, so if you followed all that, that's great. Just don't forget it. So you got to keep practicing it in order to not forget it. Okay, so go back through, add these reactions to your reaction map. Okay, so I sound like a broken record, but you really need to do that. Okay, so go back here, add your ozone and H2O. So just keep adding reactions as you learn them to your map and just let it expand out and grow your tree.